Okay, so we're going to look at Chapter 2. This video will take you through the concepts of matter and energy, composition of matter, and molecules and compounds. Since by your reaction last week, we're going to spend some time reviewing or relearning some basic chemistry principles. Chemistry is just as much a part of anatomy as the body systems. The food you eat and the medications that you take are all composed of chemicals, and you need to be aware of what is interacting with what at the cellular level. Now, before we get started, a couple of things. You need to have your notebook with you. You are required to take notes. Feel free to stop the video, rewind the video, and make sure you are getting the information. If you have questions, I am expecting you to write your questions down and bring them to class to share. We will have a discussion after each section in class to clear up any confusion. So matter is essentially everything. It is defined as anything that occupies space, has mass. Matter exists in 4 different states: solid, liquid, gas, and plasma. However, your book only discusses the first 3, so, as a quick review, and no, this is not on the slide, and yes, you probably should take note. We have solids, like bone. They have a definite shape and volume. Then we have liquids, like blood and sweat. They have a definite volume, but they conform to the shape of their container. And then gases, the air we breathe, has neither a definite shape or a definite volume. We're not going to talk about plasma for the time being. Matter can change one of 2 ways. There's a physical change. Physical changes are concerned with energy and states of matter. A physical change does not produce a new substance. Changes its state or phase, like melting, freezing, vaporization, condensation, sublimation, are all physical changes. Examples of physical change include crushing a can, melting an ice cube, breaking a bottle. The second way matter changes is called a chemical change. Chemical changes take place on the molecular level. A chemical change produces a new substance. Examples of chemical changes include combustion, which is burning, cooking an egg, rusting an iron pan, and mixing hydrochloric acid and sodium hydroxide to make salt in water. So how do you tell if a chemical or a physical changes are apart? A chemical change makes a substance that wasn't there before. There may be clues that a chemical reaction took place, such as light, heat, color change, gas production, odor, or sound. The starting and ending materials of physical change are the same, even though they may look different. When you melt ice, it's still water. So energy has no mass and takes up no space. Energy is the ability to do work. It can only be measured by its effect on matter. So you have the first type of energy we're going to talk about is kinetic energy, and this is energy of motion. An object that has motion, whether it's vertical or horizontal motion, has kinetic energy. An object can store energy as a result of its position. For example, the heavy ball of a demolition machine is storing energy when it is held at an elevated position. This stored energy of position is referred to as potential energy. Chemical energy is energy stored in the bonds of chemical compounds, atoms, and molecules. Chemical energy is released in a chemical reaction, often in the form of heat. Electrical energy is the result of charged particles moving. An example of electrical energy in the body occurs when ions move across the cell membrane. Mechanical energy, this is the type of energy that is directly involved in moving matter. When you pedal a bike, your legs provide the mechanical energy to move the pedals and, in turn, rotate the wheels so the bike moves forward. Lastly, radiant energy is the type of energy that travels in waves, like UV light or X-rays. This type of energy is often referred to as the energy of the electromagnetic spectrum, as seen in the bottom right-hand corner. Energy is easily converted from one form to another, in most cases. Elements are the fundamental units of matter and cannot be broken down into simpler substances by ordinary chemical means. 96% of the human body is made up of 4 elements: carbon, hydrogen, oxygen, and nitrogen. A complete listing of the elements can be found on the periodic table. Recently, as in a couple of weeks ago, in August, a new element has been added. Researchers from Lund University in Sweden created it by slamming atoms of one element, calcium, into another called americium. An atom is also known as the building blocks of the element. All elements are unique. The atoms of each element differ from those of other elements. Fun fact, atoms comes from a Greek word meaning incapable of being divided, and these atoms cannot be divided. When you look at the periodic table, we designate each element with 1 or 2 letter symbol, called an atomic symbol. As you can see, the atomic symbol for carbon is C, and oxygen is O. And as you may remember, some get more confusing and are named after various Latin words, like potassium, which is K, for kalium, again, which means in Latin, potassium. So now let's look at what's inside the atom. In the nucleus, we find 2 wonderful particles called protons and neutrons. Protons have a positive charge, and neutrons have no charge. As you can see, we often put a plus sign next to the P to signify the positive charge. On the outside of the atom, orbiting the nucleus, we have electrons, which carry the negative charge. The number of protons equals the number of electrons in an atom, and that's key to make sure you understand. So here we have the structure of the helium atom, just 2 different visuals. The dense central nucleus contains the protons and neutrons. In the model on the left, you have the atoms and electrons, those little gray dots, one here, one there. And we'll move around the nucleus in a fixed path designated by the black circle. In the orbital model, so that's the planetary model on the left, in the orbital model, electrons are just shown as a cloud, this very faint gray, of negative charge. You don't necessarily see the specific electrons floating around, rather just their combined negative charge designated as gray. So here we have the atomic structure of the 3 smallest atoms, hydrogen, helium, and lithium. As you can see, the difference in the number of protons are 1 proton, 2 protons, and 3 protons. So atomic number is the number given to an element that signifies how many protons that atom contains. The atomic number is unique to each element. Side note, keep in mind that the number of protons and electrons in an atom is equal, like we said previously. So if an atom, like hydrogen, has 1 proton, then it's going to have 1 electron. Atomic mass is the sum of all the protons and neutrons in the nucleus. Atomic weight of an atom is equal to its atomic mass, in most cases, if there was only one form of the atom. However, as you remember from chemistry, there are those pesky variations of atoms called isotopes, which have the same number of protons and electrons, but vary in the number of neutrons that they contain. Therefore, as you probably put together, isotopes of an element have the same atomic number, but different atomic masses. Here we have some isotopes of hydrogen and how they differ with their neutrons that differ. The first one we have here is hydrogen with 1 proton, 1 electron, no neutrons. Deuterium has 1 proton, 1 neutron, and 1 electron, and then tritium has 1 proton, 2 neutrons, and 1 electron. So we're going to discuss radioactivity. A radioactive isotope, a radioisotope, is an isotope that exhibits radioactive behavior. They're heavy, tend to be unstable, and they tend to want to decompose to a more stable isotope. Radioactivity is the process of spontaneous decay seen in some of the heavier isotopes during which particles or energy is emitted from the atomic nucleus, which results in the atom becoming more stable. You're probably thinking to yourself, why on earth do I need to know about isotopes? And even better, why do I care about radioactive topes when I am in an anatomy class? Well, radioisotopes are used in PET scans, which you read about in Chapter 1. The injection that a person receives prior to a PET scan is a short-lived radioisotope that has been tagged to biological molecules like glucose. As these radioisotopes are absorbed by active brain cells, gamma rays are produced, which are picked up and analyzed by the PET scan and produces a colorful picture. Last but not least, we're going to cover molecules and compounds. A molecule forms when two or more atoms of the same element combine chemically. For example, if you take two oxygen atoms and combine them, you get O2, or the oxygen that we breathe. Keep in mind, in a chemical equation, the atoms on the left of the arrow are the reactant, and the molecule that forms on the right of the arrow is the product. If you're confused on that, let me know. When there are two or more different atoms that bind together, those are called a compound. An example would be if you take 2H plus O yields H2O, or water. So this figure is to remind you that compounds always have properties quite different from the atoms making them up. In this picture on the left you see sodium, which is a silvery metal, and chlorine, which is a poisonous gas, yields sodium chloride, known as table salt. So that concludes your first video in Chapter 2. Hopefully you wrote down some questions, and I will see you in class tomorrow.